Okay, hopefully now it is online. Now should be okay. So let's hope that this time it will not break off, because it seems like that the internet connection is not excellent right now. I guess more people are returning to the work, and even at evening we have some problems with connection. Sorry for that. Hopefully it will hold through the session today. Okay, so I was starting talking that we will make a model today that could predict the next word for the recipes, like how to make pancakes and whatever. Like the model that can be even creative of generating recipes. And we also can use the same model for the like Bitcoin price prediction and weather prediction and whatever. So we'll first talk about a little bit of the theory, and then we'll code a few models. And then for the home, you also will have a quite fun task. So here there is a visual representation of very simple RNN. So this type of RNN, sometimes called vanilla RNN. So the equation for this one is the following. So this is going to be the equation. By the way, the green recurrent cell, so this is called recurrent cell. It's like a repeating cell. It can have like more advanced equations as well. So this is the simplest equation. So the inputs or x's in this case will be words, and this will be the next word in the sentence, for example. This is actually this task of predicting the next word in the sentence. This is called language modeling. So language modeling task. There are other tasks as well you can do with the recurrent neural networks, right? That is not the only task that you can do, but this task is really nice to illustrate the features of RNNs. So it looks like this. Hopefully it will load. So there is an input word. So what is, right? Then the next one is, D, and then D gives the problem. So it has the previous word predicts the next word. So, and you do it for every word basically in the sentence. And later when you have the hidden vector here, it is like a memory. So if in that memory, when everything is encoded, we can predict the next word based on all of the previous words. So that is quite neat feature. So the way how it would look like is like basically the way you type in the Google search engine or some other autocomplete that is based on deep learning, where you have the encoded, all of the history encoded in the H vector. So you already know about the vectors, right? So you can encode all of the information in one embedding vector, and then using that vector and the equation that I had here before, or more advanced equations, you can predict the next word. Hopefully that so far is clear. The way how it works is by using the same weight matrix. So the W weight matrix is the same for every time step. This is very important to understand. So there are not separate weight matrices for every time step. There is just one weight matrix. So there is one learnable matrix. In this case, actually, in below, if you look, there are like WH and also WX and the B, the bias, right? So those are the learnable parameters or matrices. that are the same for all time steps. And of course, also same for all batch samples, right? The other part, same for all batch samples, that we already know very well, because all of the models that we covered so far have the same weights for all of the batch samples. But in this case, there is a new dimension coming in, the time dimension. So the time dimension also, again, these weights and biases are the same for every time step. So in the very beginning, there is an additional vector, so the memory vector h. In the very beginning, the memory vector h, usually called h0 at that moment, is initialized as zeros. So we could think about it like torch zeros by the by the size of hidden size. So we are initializing our memory in the very beginning as zeros, and again the h, so the h0 is not for every sample, for every time step. So the h0 in this case is changing from every time step. In the very beginning it's h0, in the next step it's ht, in the next step it's ht plus 1, in the next step it's ht plus 2, and so on. So you pass it through this equation that you have here on the right side, and you get the next h. But at the same time, you must understand that this again is this is different for every sample in batch, right? And also different for every time step, but the weights are not different. So already we can see some that are differences and some that are not different. So these are learnable. These are different. These are not different for every time step and the sample, and these h's are different, and the x's of course also are different. So in this case, the x's are the words, like in the sentence, like we have here the x's, right? And the y's, the predictions, again, the words, so they are different for every time step and also for every sample, because every sample is different sentence. So all of the samples are not the same sentence, they are different. That's why we have these parts different. But again, just to emphasize, the weight here, and the bias here is all the same for everything. So they are like this cell, and that's why it's called recurrent, because you're using it like in a loop, like kind of, you can say. Also, there's this is also making this model slower, because as you know, convolutions we can parallelize. We can run the same kernel function to all of the positions of the image. We cannot do this with the RNNs. So we need to go from the first time step, then to the next, and only that way we can aggregate the outputs. So it's not possible to run all of this kind of function in parallel. Tomorrow we will look at some approach that can be parallelized, but this one is not. So so this is so far about this part. Let me see, maybe we will look at some other representations, visualizations, and then I will ask a question: do you understand it? If you don't still understand it, don't worry. Probably when you will start coding it will be a little bit easier to understand, but try to kind of cover the basics. So the basics, again, this is the same image as on the first slide. So we have the weight matrix that is learnable, and this is used in these graph functions. These graph functions are recurrent functions. These recurrent functions are producing new vector h that is passed into next function, into next function, into next function, and all of these functions are the same. They use the same weights, but the h in the very beginning is 0, and then it starts. This is like a RAM, you know, like read append memory. This is like your current memory that is dependent on every sequence. Every sequence, the green memory cells are different. They are not the same for every sequence. That is something that is dynamic. And the X's that are coming in, these are the like data signals, the words. And when we have those H's, these H's can then be used to predict the next word. Let me add another image, and then we'll go to the questions, because it'd be nice to understand this kind of concept before trying to implement it, at least in some capacity. So here there are some ways how you can operate with recurrent neural networks. So the one that is used for the training most often, because you have much better backpropagation properties, is this one. So you can use others as well, but this one works much better, because then you don't have such a big impact of the backpropagation through time. So there is this thing that you need to somehow get the error signal from the outputs to the inputs through the weights, and to do that, this is not easy to do. In a sense, when you have something like, let's see, if you have something like this is not easy to get the error gradient. So if you give the first word and then predict what will be all of the next words after the first word, and then compare to the ground truth, calculate the error here, and then pass that error through these cells with partial derivatives with the backprop to this like input basically. So to get the error to this poor cell here, this would not be that easy. Well, like from this cell that would be easy, but from these cells that they should like the impact of the last word will be very small. So that's why usually you don't train it with this kind of procedure. So this is what you use for the training. You can of course use this for the inference phase of predicting the next word, because if you have predicted the previous word, you can just stack it here below and then predict the next one. So for the inference, you can use most likely almost any others for the inference, but I guess one that would be interesting and fun to use is something like this probably, because this one you can start writing like you want to make a pancake, right? You need to add the flour, you need to add the milk, you need to stir it up, and then the deep learning model can say what you need to do next. So that's kind of fun. Of course, you can roll out it with the next type of operation or whatever, but that would not be as precise probably. So for inference, you could use something like this. But of course, you can use also in inference this one, even this one. So they all work. Also, in theory, they all work for the training, but for the training, this one works the best. So let me check. Do I have some other images to kind of cover this idea? So do you have any questions so far? Any questions so far? So if no questions, then minus. Maybe I somehow explained some part not really clear, because we will start coding it just in a second. Meanwhile, while I wait for some of the questions, I will add the template to the Google Classroom and also drop the link in the chat. So 13.2. So just a second, trying to find the template. And then I will check your questions if you have some, and hopefully when we'll start coding it, you will start getting some questions. Because if you have not done the time series models before, they might not be that intuitive to understand. So this will be in the 13. Okay, so that in the classroom you have the code available. Okay, great. It seems like that you don't have questions. I'm not sure. Like, hopefully that's great. So please download the 13.2 template. So is 13.2 template ready for work? And when you run it the first time, you will need to download the dataset, and I will also show that you will need to install some of the tokenizers. So that's like the conversion from the words to the representation of like dictionaries or the one hot encoded probabilities, because of course we are not working with like real words, we are working with the tokens, right? So I'm so yeah, you can give the answer in the chat when it's ready. If not, then let me know what's wrong with this. And I also will add here some note. So the X shape will look like, so previously when we looked at all of the input shapes, they were batched by input features, right? In this case, there will be an additional new dimension, sequence. So this sequence dimension is the time dimension, and we will work with all three of them. Like, so we will work, so all of the kind of operations primarily goes over the features dimension, but the sequence dimension is included in the way how the time rolls unfolds out. So yeah, I will drop the link in just in a second in the Mega as well. Thank you for reminding that. I will show you also how to work with the tokenizer library. You can make your own tokenizer, of course, there's no problem about that. So here there is the file template. Okay, you cannot download the dataset. That's interesting. So, yeah, I'm not sure about that. Let me check Drive. So not Drive, but a Dropbox. Maybe it needs to be opened as a public as, but I think it is already. Just a second. So I will try to look at it. If it will not work, then I will just give you the Mega link, but the Mega link is not downloadable automatically, unfortunately. So let's see. Anyone can see the link? Right, so we have the link. Okay, I'm not sure, like, why would it not work? You can try to get the, so you can try to get dataset from this link, dataset link. So if others also have problem downloading from Dropbox link that I have inside the code already, so then please let me know. Maybe there is some issue with it. Or maybe I need to update it actually. So it seems like this is some kind of temporary link, by the way. No, it is not. So let me check. I will try to do this in another browser. Yeah, it doesn't work. Great. So the Dropbox did it again. I was hoping that I can make a link that I can use just in the code here directly. It seems like it's not working at all. Just a second, I will try. So you can get the dataset from Mega. but I will try to look if I can get a proper link here. So no, it's not a proper link at all. Okay, so I will fix this link later. I probably don't have time right now to fix it properly. Okay, but you're still not indicating that you have the file, so maybe I should do this. Let me check. I will try to do this in a second. Fix that link so that you can work with it. Try to drop it on some of my servers. And my servers are not responding right now. That is interesting. This is weird. Okay, now it works. Just a second. Okay, I will get it ready just in a second. We'll drop it on other server. This was not expected. Okay, it's uploading, so it will take a little bit of time, and then we will use it with a different link. So yellow robot, share this one. Okay, yeah, this will work. This will work. So okay, I have a new link. The new link is in the here in the chat. We'll also update the template in the Google Classroom. This was a little bit unexpected turn of events. Just a second, upload. Upload and replace. So we have this one. Okay, we have a new mega link now. So this is a proper template link. And in the Google Classroom, I also will fix it just in a second, and then I will answer about the tokenizer, because I have a question in the chat about that. So this one is also uploading. Okay, save, great. So the new link looks like this. I will also drop it in the Jamboard probably on the slide number 4 here. So they also show you about the tokenizer, what you need to do to enable it so that you don't have errors. Okay, like that. So there are a lot of types of schemes for tokenizing. So let tokenizer. So the idea is the following. So let's have some kind of sentence here. So add eggs to the flour. Oh man, I should not write it like that. Don't know the spelling correctly. Not a native flour, right? Not a native speaker, right? And so this will be the sentence, and the tokens. What I mean by that is that maybe I should add something more here. Add the eggs to the flour, and then add milk, and okay, let's see, like that. So then it would give the same token for the name for the word add here and the add here, for example. So this would be here the same token as this one, and the tokens itself, they are in they can be some kind of embeddings or like some other vector representation, but they also can be a probability distribution. So for example, we could then have, so here we have, let's see, so that's actually a good question. So here are the 1, 2, 3, 4, 5, 6, 7, 8 words. So we have 8 words, vocabulary. So that means that we need to have the tokens, if we have those as probability distributions with 8 dimensions. So because we want to have the one hot encoded token, so in this case this will be the first one, for example. Then there is a 0, 0, 0, 0. So then we need actually 4 zeros. You can just copy it. Okay, this is a little bit too much here. Let me see, can I? Oh, I cannot do this. Okay. Anyway, there will be a little bit offset here. So this will be the first token. The same token is of course for the other add, right? So these are the one hot encoded kind of probabilities. Also, of course, they can be represented as indexes, because if they are represented as indexes, then we can easily convert them in this format, right? So the other one is x then, right? Then the other one is the to floor, right? So we need some kind of representation where the distances between the words, so if we just use the indexes, like this is 0, this is 1, this is 2, the distances between those words will be different, but this is not good. We need some kind of representation where the distances are the same between all of the words, and initially, basically. Or if we think of as a probability distributions, they are all like just having the one dimension as 100%. Or if we look at the embeddings, then the distances are the same. So the token is full matrix of, or the column. So the token is each vector. So either the token can be just a scalar index, like in this case the scalar index of 0, scalar index of 1, or the vector itself. So the x is that vector. So this is x t1, right? t0, for example. The next one is xt1, and so on. Hopefully it makes sense. If not, let me know. Yeah, so I think I updated all of the files, and just double check if I update it correctly in the Google Classroom as well. Then I will go to the next step here, and then we'll implement by hand that equation. So actually the equation also is not added to the task. We should add the equation. So that's really a simple equation. We have already worked with much harder equations. So that is this one. Okay, great. Hopefully I answered the question. If there's still something not clear, right, like just write in the chat. I will be happy to answer. No worries. So let's go step by step then. So I will also introduce you with the code template, because maybe it's also a little bit daunting. So first of all, here there is some limitations. So I have, for example, minimal sentence length, maximal sentence length. I have this dataset from the recipes that contains all sorts of recipes. I think it was like over 20,000 recipes, so, or 10,000 or something. So, and then there's we're looking just in the sentence length. So I mean, we could generate the whole recipe itself, but we are now generating only sentence by sentence. So there is the maximum number of sentences in our dataset, For the testing purposes, I use 200. If you have a GPU on your computer, you can probably like comment out this line. But in my case, I'm running, like when I run on GPU, then I actually train it for the real. But when I develop, I just use CPU here. So, and yeah, let me go through the code. So here we load the data set in, and there is some small like if statements just to filter out a little bit of those data like sentences. And we use here two tokenizing. So one is the sentence tokenizer, so that just returns words. Again, you could do it yourself by splitting and stuff, but like when you start actually looking at the language, how humans write the words, there are so many variations. So in some cases, it's not actually optimal to do this by hand. It's like yeah, so that's why there are some libraries that kind of help out, but they are also not perfect at all. So here we use this library from pip install natural language toolkit. And here how to use it is the following. So first, before using it, you should download the kind of tokenizing models, as they call it. There are some are actually much better than this one. For example, you can split your words not by words but by syllables, or like by just the common used combinations of the letters, you know. So that would be even better way how to tokenize your inputs. But this case we are trying to make it simple. So what you need to do is then to go in the terminal here. Then we write import, or we can just drop in this line, import natural language toolkit. Okay, there's something, oh sorry, we need to write Python, then import natural language toolkit, so that's importing. Then we need to write in natural language toolkit dot download. And then it gives me some kind of user interface, but if you don't have user interface, you can also get the same effect from the console. And you should then go inside, you should just type in download or d punkt. So we need the model that is called punkt, so that is like some kind of English type of default model. So, I mean, you can use others as well if you want. So it's not necessary that you need to use exactly this one, but it will be just easier if you use it. So I hope that you can get so far with the tokenizer. So I will drop that in also in the Jamboard slide number 4. So let me see what happens if I run it. Probably it will not work, it will break somewhere, but at least it should work at least some capacity. Okay, but if no graphical user interface appears, that is still fine. So because it will just give you in the console the same kind of the way what you need to choose. So maybe you can also pass the download directly to this function. Probably you can. Let me check what you have in that function. Download directory, self, info. I guess you can. I think I did not check it, but I think you can do it like just like that, punkt, and just run it, and it should work probably. So if I try to run it, so in case if the interface doesn't open. And it seems like it's working already, so it says that it's already downloaded. Okay, yeah, definitely should update again the template. This should look like this. Otherwise, with that user interface, this is definitely not the way to go. Sorry for that. I did not realize at the very beginning that this could be also an issue. So I will drop that in the Jamboard as well. So this is another method how to do this. This would be a lot better. Okay, so I will update the link in the Google Classroom as well. Not the link, but the template, to avoid problems with somebody. Okay. And let me know if you get it working at least so far. So let me check. If I run it, what will happen? So that's updated, parameter list, the sentences, optimizer. Okay, yeah. So it should fail at this line that the model optimizer, the model parameters do not have any parameters. So that means that we're good to start working with the model. Yeah, before telling more about the template and the code itself, please let me know if you get till this point or you have some problems. If you have some problems, let me know what kind of problems. So, are you okay? Point. Did you get to this point in code? So, is it working? Is it working so far? Plus, minus. If minus, please let me know what is not working so I can try to help support you. And meanwhile, I will get ready to explain the model itself. Okay, so there is a, oh no. Yes, you're right. Okay, Kristaps is saying something that is correct. We have an issue there again, unfortunately. The destination is missing, so I was updating this part and deleted this part of the code. So again, I think the third time, I just need to upload again. So here the destination part is missing, unfortunately. Oh man, but at least a lot of people are got it working. So let me see. So this part was missing. I will update this in the Jamboard and also in the Google Classroom and also in the Mega. So a little bit of struggles getting to started. So let's see. But thanks for letting me know about the issue. So let's see, edit. Where is the edit? Right. So now I am uploading a new version in the Google Classroom. So the new version is uploaded. Wait, what is this stuff? That is uploaded, and in the Mega, again, we'll have a new link, unfortunately, but no worries. It's great that you're helping out of letting me know where there are some problems. So the Mega link is coming for you. Okay, so okay. So the Mega link, I gave you also the Mega link or the template, but if you have some problems, as some of you wrote with the natural language toolkit, so I can advise you just with this line. So I cannot, I don't know, like if there are some other Conda issues, then probably you need to reinstall that library. With the Conda, it's always better to install with the Conda, but sometimes maybe there still could be some issues. So anyways, we have quite a lot of pluses that we can get ahead. So yeah, I gave you the fixes for the downloading. Okay, now we are missing the model, and below here there are some of the interesting hacky things here, but they're not really actually hacky, but at the same time really important. So let me try to explain a little bit this code here on the bottom part. I will copy this to the Jamboard and add some information. Oops, not like that. Okay. Okay, I have it here, and I'll share the full screen. So here are some of the things that are interesting. So first of all, in this code, actually in the dataset loaded all of our data as NumPy. And now when it gets loaded through the data loader, it creates everything as a double tensors. So that I need to convert it to the float tensors. So that's one. Then here, so here there are some very nice function that is used also in NVIDIA optimizations for RNNs. So these are the called packed sequences. So it's a idea that you have different size sentences. The lengths of sentences have different sizes, and you need to like pack them in a way that the end of previous sentence is the beginning of the next sentence. So like you can imagine that you want some kind of matrix where the first sentence is here, and then the next sentence is here, so this is shorter, then the next sentence again follows like this, and this is, let's say, a lot bigger. So you convert it from the form of the list or the like matrix form with the padded with zeros, because all of them are not the same size. If we put them all in just in one matrix, we need to pad them by zeros, right? Otherwise we cannot make a matrix. And this method of like putting all of them just in one dimension, like when we are combining the batch and sequence dimension, this is covered in the packed sequence. So there is like the length is batch times sequence, and the same can be also done like when we stack them just in a matrix with zero paddings. But in order to do this, there is actually a requirement that the largest sequence comes first. So that's why we need to order them. So there is a sorting of the largest sequence in the descending order, and then we pad them. Otherwise, this method do not work. So this is related to way how then later you can use it to make it much faster with the RNNs. Because you also try to process every step at once, like in a parallel. So again, if you look at the same example here, we have 3 samples in a batch, so these are 3 different sentences. When we run our RNN, what we actually want to do is run like with the step size, so just for all of the samples at once. So this will be the first step size, then the next step, then the next step, and then for the third step here, or the fourth, there is no time step for the blue sentence. So we are just ignoring that, and then we continue with the others that we have. Then at the end, only the yellow sentence is left. And also, if we have the representation of concatenating it all just in one sequence, then it's really nice that we can pass all of the sequence through some kind of linear projection or convolution or anything else, and we don't need to work with this bizarre, really hard, like zero padded method. So that's why the packed sequence is something that you should use. The way how it's used here, this is not optimal, but I'm just using in this way to not confuse you too much. Packed sequence. Usually when you want to work with multiple GPUs, this is definitely not the way how to do this. So this is one thing. Then the other thing is the weights here. So this is a weighted cross entropy. This is very, very important, because all of the the words in our data set is not equally distributed. So this is a weighted cross entropy because unbalanced data set, because unbalanced data set. If we don't have this weights here, then what will happen is that the words that are most often used, like the small short words like and, or, the, and so on, will be like learned with a very high priority, even though they are not with a very high priority as a information holders. So there is something called Zipf law, if somebody knows, that is from the natural language. And this is basically, and it says that the short words in any language are much more dominant than the long, complicated words. And we don't want those to be prioritized. That's why we use the weighted cross entropy here. And also, again, really. Hello, are you there? Did we disconnect, or are we still there? Did we disconnect? Are you still there? Oh no, what is happening with the internet connection today? This is totally terrible. This is totally terrible. And why exactly my streaming is going over the limit that I gave it? That is strange. Okay, hopefully we'll get back on. If by any chance the network drops, then I will give a new link. But this is not good at all. Yeah, I guess the place where I'm in the office in the middle of the city is not really good internet connection right now. So anyway, hopefully, but if by any chance the connection drops, I will try to give a new link. So here, let's see. So what I wanted to tell you before all of this strange thing happened is that if you look at this kind of representation, and this is much better representation for this kind of loss function and procedure, because if you can see that we can calculate the cross entropy as it would be like a simple classification task, you know, without any sequence dimension. We just stack them, like concatenate them in one dimension, and then we can compare the predicted probabilities with the ground truth probabilities. So that's much easier than using the matrix where we have zeros here, and then trying to like mask them, eliminate them, and so on. Hopefully it makes sense why this kind of representation is good here. So there is a batch and sequence or like matrix like that. And of course, every time step is not actually just one scalar value. Every time step, as you know, is a probability distribution or token. So that's again is some extra information there. So let me know if this is clear for you, hopefully. So I will drop this in the Jamboard. So is this part of code clear? Plus, minus. If minus, please let me know what is not clear in this part of the code. And then we'll start coding the actual model finally, hopefully. Hopefully the internet connection will hold. So I see 1 plus, that's nice. What about others? If you have some questions, not clear something, please let me know so I can help you out. Okay, that's great. There's another question about the, so if you, yeah, the minus sign. So yeah, I think you're right. It would be nice to have, be more precise, to have minus sign probably in inside of that equation, but the output will be exactly the same. Like, I mean, if you calculate the mean value of minus values or the mean value of the plus values and then add the minus sign, that's the same output. But that is the cross entropy, right? You remember we worked with the cross entropy a lot before in the previous times. So that is nothing new, hopefully, for you here. Maybe I can find the equation for you. Where is the equation? If you want the equation, I could try to find it or write it my own. If I write it my own equation, then it might take a little bit more time, but probably I should do it. LaTeX it. So the math call, the sum of this thing, just a second, I will share it in a second, plus epsilon. So the minus sign location can be either way. Copy, because, okay, there is maybe one caveat there, because the outputs will always be limited from like, so if you look at logarithmic function, maybe I should point this out, maybe that's why this question is here. So let me check when you work with any functions, you need to know what are the input data limits, right? If you just don't put an output limits, you don't know what you're expecting. If you know the limits, you definitely know that nothing bad will happen, and they will work as you want. So if I look at the logarithmic function, it looks something like this, depending on the base, right? So why it's not loading? Okay, just a second. The Google is not loading image for me, unfortunately. Let's check this one. But the Google have really nice Jamboard. Okay, it's still not working. Oh no, it is working. Right. So if you see here, the probabilities will always be from 0 to 1, right? In this range. So the probabilities never will be over 1. Never ever. So that's why this function will work great even with the minus before or after the summation or the mean value. So this equation again is not exactly what we have here. Maybe I should fix it. So frac 1 divided by n, and again, I already told this many times, but maybe before you were not able to really grasp it, is that the summation or the mean doesn't matter at all. So it means that, like, if you have the mean here, that is just a very nice scalar for the batch size to have the same learning rate for regards to like any batch size, but there's still again some issues it's not that simple. But okay, there's another problem here, epsilon. Today really not. I was yesterday my car's engine blew up on the road, kind of not really like totally wasted, hopefully not, but and that happened in the middle of the night when I was driving. That's why I'm not maybe too sharp right now, but still hopefully sharp enough to finish this tutorial nicely. So we're going again, seriously. Okay, hopefully the internet will hold. So the equation here, the range of our values are from 0 to 1, right here. And if you think about it, that means that all of the values always will be negative. And if I add the if they match, then there will be 0. And basically we want that they will be matching. So hopefully that answers the question. So this is a probability from 0 to 1, right? To 100%. And that's why this loss function works. Okay, really hope that this covers it. So let's go finally to code this stuff. So before the internet dies, right? So, okay, let's see. We have the code. Yeah, the car accident, not very nice. I still hope that it will not cost like a huge sum of money. Like it was, it's a funny thing that the car was with the metallic chain, so it should not like break that easily. But I guess they make in nowadays the engines with metallic chains that are like not very durable. So anyways, let's write here the stuff. Hey, great. I'm really happy that I answered the question for Armand's. So anyway, here the RNN cell. So we'll have some kind of cell block so that we will repeat many times. By the way, in the task that I gave you just, I have also a nice schematic of the task. I should also drop that schematic here, otherwise maybe it's not clear. Where is my schematic? Just a second. We'll find it. Okay, I found it. Hopefully. It's not working. Again. Yes, now. So we want to build this kind of model with 2 layers, the 2 RNN cells. So great, interesting information in the comments. If you know some additional information about cars, you can share some links. So anyway, yeah, but some time ago, actually, the chains were so good because you could drive forever with the engine. So anyway, here there are again some other representation that I forgot to show you before. The idea that you have different length sequences and there are the paddings, right? So we will feed this to this RNN model, and in this part, middle part, we have a loop here, right? And in these green parts here in both sides, these are just basically a fully connected layers or linear projections. The first projection is the way how we always do it, and the second projection is just transposed to even more enforce the connection between the hidden state and the actual input wording vector or the token. So we're kind of using the same matrix twice in our model. That is really cool. So what I mean is that like when we're talking about the accumulation of the gradients, right? So if we pass here this model once, we get some error gradient, then we, when we pass the error from that side, and if we pass it again, we get another error gradient that is summed together with the previous one. So what I mean is there we got some error here, and we sum it also here. So it's summed in 2 places, so it's even better. So that's one thing. And these linear projections, they have one very interesting optimization feature, so that we can use in the first part of the model. So that's called embedding table. So we will code that in just in a second, and you will see how it works. So maybe I should somehow point it what it is. So this part of the model is this one. So we can write it either by using the notion that we already know, like dot product with the wx, right? Dot product. So we can do this, or we can do this, because in the sense of when we have all of our vectors as just zeros and ones as the one hot encoded vectors, then this doesn't make sense anymore, because we can just select one row from the embedding matrix, and we don't need to do the expensive matrix like operation. So that's why we use something called embedding table or embedding lookup table or whatever. where this is actually the same procedure as it would be as a dot product, but optimized. So the model itself is not difficult. We will try to code it just in a second. Not try, but will code. So, and I think probably for the homework we will not be able to finish everything, so I will give some other task interesting for you. So anyways, let's code it. So there will be the RNN cell, that is that yellow box in the middle part, right? So the cell will have the input size and the hidden size. Usually, yeah, they can be different, so let's keep it different. So input size, hidden size, that's one. Then let's store also those values, so self input size will be stored. Maybe we will need them, hidden size as well. Then we will need to have two matrices. There was one, if you look at the equation, in the equation, so let me see what was the equation, the naming, WH and WX, so there will be self WH matrix, torch and N parameter. So I think we already used this kind of syntax where we have learnable parameter that we can learn. I think when we made our own kernel function, remember? We made our own convolutional kernel function. So torch, there will be a torch float tensor by default. I think it will be not initialized, and then we will initialize it. So there will be the input size mapped to the hidden size, and this will be uniformly initialized by standard deviation of the kind of, let me think. So some of publications say that it would be nice to, like, that they have some advantage if you initialize it in the range of the 1 divided by the hidden size squared. So it's actually not really proper standard deviation, but just the deviation for the uniform function. So there will be the mat function. Okay, I need to import the mat, so like that, and sqrt of hidden size. So by the way, again, this part maybe can be left out. You can just use uniform without this thing. It should work as well. But with this, it should work better. So this part. Then the next part is this was WX. WH is the hidden size. And then we have the bias. So self bias. It will be again torch parameter. That will be initialized as zeros, right? And now my usual question, right? So what should be the bias shape? So what should be the shape of B? So if you look at the equation on the first slide of the Jamboard or in the task, right, there is an equation that we are right now writing. So if you know how the matrix operations works, and you know how the deep learning works and how these models work for the last at least 6 sessions or more, then hopefully you can answer this question. Do you have any ideas? If no ideas, then type in minus. Again, if you look at that equation, like on the slide number 1, that equation is something that you have seen many times before already. So you should be able to understand what it means. And so there is a dot product between the W and H, and then the W and X. And then I need to add the vector B. And what should be the shape of that vector B, the bias? Come on, guys, I know that you should be able to at least guess it if you don't still understand it. Maybe if you will, if they're depending on the answers, okay, you have minus. Oh man, okay, but thank you for giving a feedback, at least then I can explain it again. So, okay, let's see. I will try to draw the situation on this slide number 7 in just in a second, because I was hoping that you will answer this so quickly that I even don't have time to draw it. Just a second. Thank you at least for the honesty, but I would be really happy if you would know the answer. So, so here we have the equation. So we'll try to draw it in some kind of linear algebra way. Probably I will draw it a little bit not correctly, but at least it will hopefully be understandable. So let's see. So we have the situation that we have some kind of let's start by x here. So we have the input of vector of x, very large input vector of x, right? So this is the dimensions of all of the, for example, the words. So words dimension. So this is let's say 10,000 words, and this is xt, right? So this is our vector, right? Then we have the matrix, of course. The matrix Wx here is something like this, for example. And if you look at the shape, how it looks like, right? When we do the dot product, we will get out from this dot product here this size of vector. So this size of vector will go out of that matrix operation. So, and then we can transpose this vector, right? We can make this vector like, okay, can I do this? Why it's not working? So we can transpose it like this, except this must be like that, right? So first we do the matrix multiplication here, the dot product, we get the vector here, then we transpose it like this, and then we wanna plus it here with the b, right? So, and what do you think, what shape then this b should be so that this operation would work? Does it help? It help any ideas of a shape for b? So maybe I should write it step by step. So this is x, so this is the first step. So this is then so this again is also the first step. So this is w, and this is at the first step x, and this is then the second step, what is coming out, the output. And then the third step is when we transpose our output transposed, and then we do the arithmetic addition, pairwise arithmetic addition. So what shape should be b in our context? So we have only two shapes here. So one is the input size, another one is the hidden size shape. So what do you think, what will be the shape of that b vector? Interesting answer. So yeah, so okay, let me also show so that okay, the other part of the equation here, the first part is okay, why? Okay. So the first part of equation is using the previous time step h, and by default the previous time step is actually 0, right? So I don't know, like I don't know how to write it like this maybe. So there will be the previous time step h here, and the matrix for that one looks like this. So it is the same size matrix. So this is the same size matrix, right? And the output of this matrix, of the dot product, right, will be the same size as the input, because that is a square matrix here. So that is for the WH here. So this is for the WH, and this is for the WX. And if you already see that this part of the equation, yeah, so the matrices can, but this is, B is not the matrix, by the way. So here, these should be added, and this is not, again, so I'm trying to decompose it step by step, but I guess I'm failing it a little bit. So I will like split it in 2 slides probably. So hopefully I can somehow copy everything on this slide. Unfortunately not, I guess. So, okay, so let's see. So after doing the first, so if let's delete stuff and go again one step back. So we have the x, the green vector, the h0, this vector. So this will be, let's say, let's have it in the color blue, and this is orange, right? And the output of these dot product operations. So these are dot products, right? The scalarized matrix resonance. Dot here and also dot here. So this is, if we look at the mathematics of this equation, first you need to do these 2 dot products. You cannot do anything else before doing these 2 dot products. So we do those dot products, and what we get is, in the next slide, we get, for the same equation, after doing those dot products, 2 h vectors, so from this one and from the other one, except I cannot, okay. Usually you transpose them so that they would be something like this. So we forget about the batch size again. So the batch size is something that is not needed for understanding this equation. So we have those 2 as outputs from those dot products. And now my question is then, what is the shape of the B here? Okay, you say the shape of the HT, that is correct, right? But the shape of the HT is already known, so that shape is the hidden size shape. So hidden size shape, also this one is hidden size shape, and the X shape is much larger here. So the input shape, so the input might look as in the previous slide. So, or is it like green, like very large vector? So if we do the dot product with this vector here, we get out this kind of very nice vector that we transpose. And this is much smaller vector, right? Because the dot product will work with the columns and rows, right? And here the same H was already coming in and the same coming out. And then the B, now we need what is the shape of that B, and Armands is saying it correctly, because the shape of the B, the only way how this could work is if it's exactly the same shape as these H vectors. So the B vector should be the same size shape here. Hopefully it makes sense. I really hope, but like I'm trying really hard to explain this already, I think the third time. This is just a linear algebra. We already did this from, I think, the second lesson from very beginning, the trying to do the dot product yourself. So if you did not do like implementation of the dot product in NumPy, like the for loops and whatever, so then you don't understand how the dot product works, and that's why maybe you don't understand the shapes, because as I said, you can change the size of that vector, or you can, in other words, you can project it with some kind of projection matrix that is W to other type of vector that is smaller or bigger. Hopefully this is understandable. So is it clear? Plus, minus, if not something clear, please let me know what is not clear there. Okay, I think Armands, who answered correctly for the hidden size idea, at least idea, get it, but what about others? Hopefully others also get it. So this is like the key thing that you always must understand with regards to the dot products, and that dot products is actually not the hardest operation here. So, okay, let's go back here. So that means that the hidden size, like this vector should be the size of hidden size. Happy to see that you're on the board right now, hopefully. So the B vector is initialized by zeros as always, right? So that's fine. Then the next part is the forward pass. In the forward pass, there is one fun thing here. So is that we can simulate the rollout. Probably I will talk about this next time, very beginning of the lesson, because we don't have time today. Is that you can have the hidden size from previous memory, right, and feed it many times over, like, and basically you don't need to initialize them by zeros. You can use some like value from the previous memory, right? So that's why we want to keep this as an option to enable, like a parameter that we want to enable for later. So let's call if hidden is none, then we will initialize it as 0. So torch zeros, or maybe we can use the same syntax as before, float tensor hidden size. Oh, here we can use the self hidden size 0, and then we also to the device. So because this should be also moved to the GPU. If we don't move it, then it will not work for the GPU. So that's great so far. Then the other part now here is the, so we want to accumulate the outputs. So there will be the outputs like that. Maybe you should also change it in the bottom part. Okay, let's call it H out. Because the outputs actually are the same hidden states, but just for each of the time steps. So here the input of X is the packed sequence. Okay, we need to unpack it. Sorry for scrolling, I will get back. Unfortunately, we need to unpack it if we want to code it by hand here. So the batch first, again, this is really interesting because here will be X unpacked. You will see why many times actually the people use not batch first but sequence first, because the sequence first is easier for this operation that you will see just in a second. So if we have this packed sequence, we want, remember from this one dimension, right? We want to now have it padded with zeros. So this function means that convert from optimal sequence, how we could call it, data holder to zero padded version. So this is why it is like that. So this is line. Hopefully it's the same. Okay, and now what we have here, the X unpacked size is actually the batch, comma sequence, comma features, right? And the features are actually the input size, And the sequence here is really critical thing. The sequence is changing depending on the batch. So for example, one batch could be with the longest sequence of 100 words in the sentence. Another batch, the longest sequence can be 10 words in the sentence. And then in the same batch, maybe there is some sequence of 5 words and so on. But we want to go by the actually by the sequence dimension, not by the batch dimension. And this is one of the reasons why usually these time series are permutated or transposed in a little bit different manner. So they don't use the batch first often. So in this code that I gave you, we use batch first, but many times you will see the code where you don't use the batch time first. So here there is a permute, 1, 2, like that. And the output now from this will be sequence, batch, and then the input size. And this enables for us to do the for loop and work with all of the batch samples at once. So this is what we want. We don't want to have 2 for loops. We want just 1 for loop. So here we'll have the xt. This will be the time step in the sequence, X sequence here. So each xt now, the size of each xt, by the way, sorry for not giving you the first part of the code. Nobody told me in the chat, so I will drop that part in the Jamboard. So here the xt size is the batch comma input size, and now we're working with very simple, very common the format of data that we already worked many times before with the regression and other parts. So this format is really easy now. So here, if we look at this format, what we want to do is to calculate the next h. So the first, the hidden here is the hidden, right? So maybe, okay, let's call it then the h. Yeah, so this will be the next h. So h, let's call it hidden t. So that will be the next one. Or we can just use it hidden, doesn't matter. So torch tan h. And here we go with the equations. So let me check. So we should use the self vx, well, and this will be with the xt dot product. But I think to avoid transpose, we should do it like this. And also then there will be a plus the other one. The other one will be the hidden. The hidden, by the way, I need to also write it down here that, sorry, there is a mistake here. So the one is, we're missing the batch size here. So x size 0 is the batch size. Maybe I should write it down so you don't be confused. So batch size is this one. And we want this to be, again, not coded as a hyperparameter. If we code it as a hyperparameter, then we cannot use this model for running just one batch sample by one. So here the output is, of course, this kind of size. So this is a batch comma hidden. And here we do the dot product with this one. And then the last one is the easiest one, so the b. So like that. And Then we need to add all of those to append to that list, hidden, like that. And for the output, we also need to stack them. So there will be the, let's call the last part as a tensor h out, and this will be torch stack those tensors together, h out, because they are all the same size. If they would not be the same size, this will not work. So then we also want to permute it back to the batch first. So 1, 0, 2. So this will permute it back to the batch sequence and the input size, like that. Hopefully this part is okay. I'm not totally convinced that it is, but I hope. Let me double check. It should be okay. Maybe there is some error. If there is some error, I will fix that in the Jamboard and let you know. But now I'm dropping this to the Jamboard. By the way, again, there is a problem actually. So the length is a problem, and also the output should be a packed sequence again. So we have two problems. Just a second. We can solve those. This is not too difficult. So this is not optimal because it includes also the hidden states of the where you don't have the length. So, but I don't want to make this code too difficult, so I will just write it here. Not optimal, because calculate hidden also for parts that should not be included. This will work because we will ignore those parts that should not be included, because we will then use the packed sequence that will ignore all of those parts that should be padded as zeros. But now, like, I just don't want to make this code too difficult. So let's add it like that. And now we need to get back to the packed sequence. So to get back to the packed sequence, let me check how to do this better. There was the function. I really don't like those functions because they have the same, very similar names. It's very easy to mix them up. So I don't want to mix them up, so I need to look which one was it. Packed sequence, padded sequence. Crazy naming, like why they made it so hard. So packed sequence, there will be the THS here, then will be the lengths here, then will be the batch first through. By the way, the fun thing is that we could probably skip this line and just use it as it is, but better not. So there will be the TH packed. This will be the output. So the packed sequence is an output. Again, the optimal kind of compression, not really compression, but the layout of the data. So convert to optimal data layout. Hopefully this part will work. Maybe there is a small bug or something we will fix then this. So I will drop this also to the Jamboard. So this is the main idea of the recurrent neural networks. As you see, we use the same weight matrices, except there is a first bug that I see. There should be H here. So the same weight matrices for each of the time steps, and we also use each time step for all of the batch samples. So kind of need to get around the shapes of the data, like batch sequence input, and then it should be quite okay to work with. So now we are just missing a very short part, basically, here in the model. So in the model we have the embeddings first. So there will be the embedding matrix. So this will be the embeddings, torch and embedding. This is again the same thing as a simple linear layer weight matrix, but we just want to make it a little bit more optimized, so we don't have the dot product with one hot encoded vector. So dataset full max classes tokens, so that means how many tokens we have for the words. And then there is embedding dimension. This will be the RNN hidden size. And now we'll have the RNN itself here. So let's write it by layers like that for in range of RNN layers, and have those layers connected. Layers append RNN cell. Oops, RNN cell like this. And here it's kind of easy because the input size and output size will always be the same, RNN hidden size, but you can imagine that the first layer can have different input size. For example, if we don't have embeddings in front, so hidden size, like that. So that's easy part. Then we need to have them as the self RNN and torch and sequential, where we will pass all of our layers as parameters, like that. And then the last part, I think, there's actually no other last part. I think there is, that's about it. Right, hopefully that's about it. So then the forward pass here, this will be a little bit tricky because we will need to use the packed sequence. So, but at the same time, it's much easier than not using the packed sequence. If you not use the packed sequence, this will be much harder. So EMS, so there will be embeddings, self embeddings forward of the X data. So X data is the part where we access the data like compact represent layout of data. And here we also want to do the argmax by dimension of 1 because the current representation of data is in the one hot encoded vectors. So X shape is batch sequence by the classes of words. But what I want to do is to have X shape as batch sequence where every sample is index of words of class. Like that. So that's what I want. That's why I have the argmax here over dimension. Maybe I have the wrong dimension here. I need to check it. So let's see. So this will be the X IDXs or X. Yeah, let's call it X IDXs. I will debug it and check it if this is correct, because if there is a mistake, then it might still work, but it will have wrong results. So this part, I forgot one issue here. So I return here the packed sequence. I forgot to add, okay, no, it will be fine. It will be fine. So the hidden vectors are the same for that one. So, okay. So there will be then the hidden, or the, yeah, so these will be the hidden actually. So self RNN forward of the packed sequence. So there is a question about the homeworks. So The next week is the last week for the course. We will look at the very also kind of challenging, complicated models with reinforcement learning. This week we're looking at time series. So for the homeworks, I will try to like grade them till tomorrow what we have so far. But in general, like as long as you finish the homeworks, let's say in like 3 weeks or whatever, like. It'd be good. I will also add to the Google Classroom like exact date deadline. I will get in contact with the university and arrange like what will be the maximal like deadline that I can give you, because a lot of you are like struggling. But still, like I hope that it's always better to try to do those homeworks sooner than later. So. Here there is a RNN forward of the embeddings, so there's the embeddings, but we need to then convert them back to the packed sequence. So this will be then M's sequence, and this will be then the packed sequence, a class here. Data, we'll copy data from embeddings here, but other properties we will copy from the previous one. So the batch sizes will be the X batch sizes, and the sorted indexes will be X sorted indices, right? So this is the way how you can get the packed sequence through the any kind of projections, like linear layers, nonlinear layers, these convolutions, whatever, and then get that to the RNN back. It's much easier than trying to do this with padding and masks and all sorts of crazy things. But sometimes you actually cannot do. So sometimes you need to do that. So here there is a hidden like that. That's good. That's good. Then the next step is we need to have the y prim log it. And as I said, we will use the hidden of that one, data, and have the dot product with the same matrix that we used for the embeddings. Wait, just transposed. So the transposed matrix as we used in embeddings. By the way, the OpenAI GPT type of models also use the same approach, but much stronger models that we will look tomorrow. So y prim is then torch softmax of, maybe I will add another lesson actually, because otherwise we are thinking we're running out of the time. So dim, so this will be then over dimension 1, because the y prim logits now are all in the same dimension. So here in this case the y prim logits shape is the batch multiplied by sequence comma features. That's why it works. So like that. And then we need just again to do the packed sequence at the end. By the way, the packed sequence situation is only because we have different like length sentences. If all of the sentences would be exactly the same length, or you have time series data with exactly the same length, then you don't need any of the packed sequences. You can just reshape the data, and that would be like so much easier. But there is no way out of it if you use the kind of uneven data, you know. So this part should be ready. And if there will be no bugs, then I will share the code also. So if I try to run it now. So this is exactly the same model that I gave you in the task. So okay, here do you have first problem. So what is the problem? This should be returning. What is this? So there should be a hidden state. I already opened the hidden. I already give the hidden state to positional. Parameters should forward takes 2 positional parameters, got 3. What is this? So forward RNN, the hidden state, right? Where is my RNN? Okay, so no, we have the X and hidden state, right? So this is correct. Okay, but the sequence do not like the hidden state. Oh man. Okay, so I guess the best way is just to delete the hidden state here in order to make it work properly with the hidden state that is for the rollout. Then we need to change a little bit the model. So now it works good. Let's see what other we have here. So X size, of course, this is not the correct now. Of course, this is not what I wanted. So the batch size is not matching here. Let's see. So what we could do is we could move these lines a little bit down the road here and take from the unpacked size. So and if this will work, I will update the Jamboard as well. Okay, now it works. Okay, yeah, so the accuracy is increasing, the loss is decreasing, and it starts generating all sorts of interesting recipes. So you could run the pudding under the boiler to caramelize it and stuff like that. So kind of interesting ideas what to make to eat. If you're using a gas grill, if covered charcoal lightly or something, it doesn't make sense much right now. Mainly because we have a very small data set included. So I will show you just in a second how you can make your own natural language model much stronger. So first of all, I will update the Jamboard. So the forward pass had a small issue with the batch size that I resolved. And then the model code also works now fine, but it's definitely not optimal, and also it's not friendly for the rollouts. So when you have the rollouts where you kind of give the first letters and then predict the next, first words and then predict the next, there should be a little bit different kind of structure, but it's not important at this stage. So I'm adding those parts also to the code. Okay, so I think because today we're also running out of the time, I will give for the homework a similar type of equations that we try to do today. So here in this part we have the very simple 10H vanilla RNN equation. So this is called vanilla RNN equation. But I will give you a little bit more advanced equation, and you will need to implement that equation yourself using basically the same template as this one. And if you want to train your model to generate really interesting recipes and share the generated code, generated text, you should remove these constraints. Like say that you could train on the Google Colab with all of the dataset. Dataset is very big, so it will take a long time. And also when you train it on CPU, it's just using very small amount of data. That's why it's not giving you perfect recipes, you know. So I hope that today this model was interesting to look at, and you kind of understood what the RNNs are and how they work. I will give you another equation for home, how to modify this code. Also, if you want to get better results, I highly recommend to do the histograms of the word counts and delete the words that are very rarely shown, so you can replace them by some kind of wildcard, like I mean, so just something that would be better. Also, you can remove punctuation. Also, using the natural language toolkit, you can also, yeah. So the last one is basically the same as the first one here. So there are some things you could do, but these are optional. So those are optional, but for the homework, I will give you another equation here in this part, and you should be able to get along with it because you already understand how to build this part. And we got pluses today regarding to the linear algebra, so I really hope that we finally got it. So just to clarify again, if I go to the Jamboard here, here we have the code that you can finish the tutorial, and here there are all of the examples, all of the explanations. So hopefully that's good enough for today. So we'll meet tomorrow. Tomorrow we will look at more of the RNN equations and the way how you would roll it out, and we'll look also at the attention models. We'll see how far we can get, but there are like some really powerful models called transformers that do not use